Great. Thanks, guys. Thank you for welcoming here to give you a talk. I think I'm really excited about robot learning. It's captured my attention for the last 6 or 7 years now, and I'd love to share a bit about what I've learned so far and kind of my thoughts a bit on why end-to-end robot learning is one of the most promising approaches for how we might scale and make robotics useful in the world. And before I start, I'd like to just give a very quick disclaimer that I'm a fairly opinionated person, and today's talk, most of these thoughts only reflect those of my own and not necessarily those of my employer. Um, this talk will mostly be two kind of parts. One is the first part will be a bit more high level. I'll give a brief overview of what the kind of robot learning landscape now is to me, and as well as a couple of different important areas of research that I think are particularly interesting, and give some arguments for why I think end-to-end learning is a very interesting approach that I think is being understudied right now. And the second part will be a bit more technical. I'll dive into some recent work from our group and then hone in on a few future problem areas that I think would be very exciting to keep a track of. Briefly about me, thank you for the great introduction. I did my studies at Berkeley. Afterwards, I had a few stints in robotics, in computer vision and portrait segmentation. But I think throughout the process, I'm really excited about the problem of decision making, where kind of intelligent agents need to make decisions that affect the world, that and in turn affect the observations that the agents need to think of. This very non-stationary learning problem in dynamical systems is very exciting to me, and one of the reasons I keep coming back to robotics. As I'm sure most of you know, deep learning has really seen a lot of successes in the past years. And there's almost this formulaic approach where a kind of baked pipeline approach that has learning in, if at all, in small components, starts with something like speech recognition. You break up a large, very dense, data-rich segment into smaller components. You break those components, process those in a pipeline, you pass them on until you finally have the end output again. What we see with deep learning, or aka end-to-end learning, is that a lot of these parts can be replaced completely by a deep neural network. And the question that I'm very interested in, as well as my group, is what happens when you kind of expand this paradigm to larger settings? I like to really use Andrej Karpathy's software 1.0 versus software 2.0 metaphor for this. In software 1.0, this is where you have humans actually inputting hard-coded instructions, perhaps in assembly or C++, getting the program to do what you desire. This is, you have some kind of human inductive bias. You have some prior of what you think the data should result in, and then you spend blood, sweat, and tears with programming, with verification, with integration to kind of deploy these handwritten instructions and hope they do what you hope they do. In software 2.0, this is when you actually have to try to automatically automate increasingly large portions of this development process. We've seen this from the previous slides in a couple of different fields, ranging from speech recognition, machine translation, computer vision, and even in those fields where you have the software 1.0 being the glue that holds together most of these big, large neural networks, these high capacity representations. Increasingly what you see is that software 2.0, this learning part that you just trust to the black box, increasingly expands across these pipelines. Going back to this slide for a bit, you can imagine perhaps if it's 2016 and it's computer vision, maybe you don't have a complete black box for this entire pipeline going from pixels to labels. Maybe you're using it for each one of these individual transitions you can think of as a completely separate subfield of computer vision. And you have learning folks who are working on learning for those subcomponents. But then over time, as you see, is that when you have a system that depends on scaling, that depends on improving via more data, any component of that system that does not scale with data will eventually become the bottleneck. And I see what this happened in computer vision is that then the entire net system became a black box, so to speak, in an end-to-end learning where the gradients flow all the way back through. And I think the reason this is exciting right now, today in 2022, is that this same transition is happening not just for those subfields, but other fields as well. Andre Karpathy, even though he left OpenAI in 2019, I think, recently last year, OpenAI Codex, with their Codex program, was able to kind of use these autoregressive language models on the GitHub data set to actually improve code generation. I think right now it's actually being deployed in some small scales at GitHub, at Microsoft, at OpenAI, and some preliminary numbers. I'm sure they're kind of fluffed up a bit, but if they've been increasing programmer efficiency by 20 to 30%. This is literally where software 2.0 becomes it goes from the data to the program, where the program has now closed its loop back to the data itself. I think this is particularly exciting, and this trend is not just in language models or code generation and code auto completion, but in other fields as well. So the question my group and I'm interested in is, if this same trend has happened in all these other fields, when or why, how does it happen to robotics? And I think there's been a kind of discussion in the literature for a few years now, to various extents, on why robotics might be a different it's a different paradigm. There's different learning challenges that might not be a great fit for end-to-end learning. And I think right now I'd just like to address a few of those. But before I do that, I think it'd be great to kind of lay out what the different options are right now in 2021 and 2022. What are people doing when they're applying robotics in the real world, and how are they applying learning to different parts of this? It's definitely a spectrum, as I mentioned before. And I think starting from the left, this is classical robotics. This is what's been tried and true. It's been working for decades now. This is when you try to understand your system, you try to decompose your system into locally linear dynamical systems. You're operating on raw state spaces. You have very good localization. You have very good kind of state estimation to make sure that you can understand all of the low dimensional factors that go into your optimal control learning system. In the middle is when you start actually swapping out a few of those components to use learning. For example, maybe you have a perception module. You rely on an off-the-shelf, state-of-the-art object detection system. You use that to generate bonding boxes, and you just add that to kind of a low-level feature that you use with some kind of closed-loop feedback, some optimal controller. And then on the right is, the completely fused perception and control. This is when you have a large, high capacity neural network going directly from raw observations back to control outputs. Various industries are sit along this axis in different ways, and I think definitely what's been done in the past decades is far towards the left, where you have very controlled, very not changing very often environments, manufacturing, industrial robotics. You have packaging and fulfillment robotics. Even Boston Dynamics, with their very amazing videos for their media releases with like dancing robots, or like really cool like advertisements for what the capabilities of the robots are, doing backflips, opening doors, climbing over unstructured terrain. What happens on behind the scenes actually is that a lot of these are still, hard-coded trajectories, and using trajectory optimization, very little learning, they can still get the robots to do very amazing things. But that's because even though the environment looks like it's extremely challenging and changing, in these kinds of very constrained lab settings, they're not. And so I think the blooper videos show that, they'll try these backflips hundreds of times and then finally get one right. And I think this works well for these settings, right? If you're you have a factory and you wish to construct your Tesla vehicles, and that the models are only going to be changing every year, it's probably the best optimal solution in both the financial and the technical sense to use kind of a very classical based method where you're very efficient, you're maximizing for speed, for energy usage, and that's where I think these kind of methods really shine. Where you start extending is when perhaps a set environment starts changing more. If you're in an Amazon fulfillment center and your packaging and the warehouse layout is changing perhaps quarterly as inventory flows out, these Roomba like robots that go and depalletize these and move these packages around the warehouse need to have a very good understanding of the environment, but also need to adapt and have some kind of autonomy in terms of planning or figuring out what the most optimal kind of strategies are for making sure the warehouse runs smoothly. And then as you start moving into more and more unstructured, unknown environments, you have self-driving, you have different kinds of, I think Skydio, I think their drones have some of the best, as I'm aware of, following users or, path planning, all of that stuff. As you start having to deal with more uncertainty in your environment, you don't have good localization. You can't necessarily run some SLAM on board and know that my warehouse isn't changing, my car assembly line isn't changing. That's when I think you really have to start using learning in more and more components. Tesla, is further right than Waymo because they actually, they don't use LiDAR, they don't use dense mapping. They actually are using a large growing data set to go directly from car observations to some lower level planner. They still use planning. It's not completely end to end, but it is more end to end than say Waymo or Cruise, where they do have some local map of urban environments, and they are kind of saying, okay, what am I seeing now from my learned perception modules? How do I put that back to a map of the world I understand, and from that map, then I can kind of bake that into very high confidence local planners that I'm using. And then on the far right is where I'm most excited about. It's where we're not making any assumptions about the stationarity of our environment, of our test time data distributions. We can try our best to kind of do whatever we can during the training time to make sure that we can learn the right inductive biases, use the right priors. But at the end of the day, it is a very challenging test time environment that we're operating in, that we need to be able to operate without any guarantees of like what the environment might look like. And I think to tackle that kind of difficulty, a learning-based approach is quite important, that don't make any kind of hard-coded assumptions that these scenarios on the left and middle might. I'll emphasize though that I think this is not saying that today we are ready to go to this green star. It's saying that I think if you look further in like 10 years, 20, 50 years, that this is where the world should or will end up in. And the question, I guess, is like, what does that timeline look like? How do we navigate, given that we have many economically viable use cases already, where the left and middle section of this chart already provide a ton of value over like very entrenched incumbents. But I think what I'm interested in is how do we steer ourselves and gradually bring everything over to the right. This is perhaps not widely accepted, but I think there are 4 main reasons why I think that this is the way that we should be going. The first one is why not? The second is that there is kind of a naturally inspired basis for why this could be correct. The third is that it's very difficult actually to keep sticking in that left and middle section of problem regimes. And the fourth is Richard Sutton's bitter lesson about scaling. The first one is, there is an existence proof. There have been applications of this end-to-end learning-based methods in a few groups, including our own. This here is a few works from our group. Starting from the top left, we have QTOpt. This is what was 4 years known ago is the arm farm, where we have dozens of robots doing indiscriminate grasping from bins, doing this around the clock, dozens of KUKA arms at the time, in a room, picking hundreds of different objects for months at a time until you have a learning-based system that can generalize the over 99% of unseen objects and be able to grasp them. We kind of extended that to locomotion in the middle. We have MTOP, which is a multitask version of that system in the upper right, where instead of just picking any object, perhaps often choosing the easiest, we have different tasks where you say you have to kit different objects onto another segment. You have to pick and place. You have to understand a bit more of what's actually going on besides for just memorizing all of the data you've seen in the past to do the easiest indiscriminate grasp. And then in the bottom, BC0, this is kind of an imitation learning version, still using months, hundreds of thousands of human demonstrations. How do you learn a multitask behavior cloning policy that can achieve many different interesting tasks, including tasks it's never seen before. I think all of these systems are end-to-end in the sense that the final policy is directly going from pixels to control actions. And I think it's very exciting that they're able to get very strong performance, especially in scenarios where you don't have many guarantees. If you have a new object, a new table, you have a new command perhaps that it's not seen before, a new configuration of objects, this is when a less end-to-end method might struggle, but these methods are able to rise to the challenge there. The second reason why I think end-to-end learning is quite compelling to me is that it's biologically plausible. Maniam Srinivasan's lab did some very interesting research where they have honeybees try to land on these like small cones, these small funnels. They painted a spiral on the inside of the cones, and they found that the bees would kind of use a visual odometry by looking at the rate of expansion of the spirals as it's going into the cone to kind of figure out how fast the bees should fly. And so they found that if they actually added perturbations by spinning the cone slower, faster to increase the rate of expansion of the image, the bee itself would actually fly slower or faster. So, besides for fused perception and control in bees, humans actually also have similar kind of heuristics. Professional athletes, if they're tracking a baseball or a football flying at them, there's something called the gaze heuristic, where the human fixes the gaze on the ball in the distance, and they try to keep where the ball is constant in their frame of view. And as long as they keep where the ball is constant, they know that by slowly accelerating or decelerating, they're going to intersect and catch the ball. I think there's also different examples of where this fused perception and control happens, but it's just interesting to see that perhaps under the hood, our own brains might be doing some of these, this end-to-end style of control in some scenarios. More important, perhaps, is that oftentimes trying to map our very complex changing world into a more constrained scenario that we can understand it better is often quite challenging. Take, for example, when we see an image of a cow and we ask, like, how do you know this is a cow? If I ask you right now, you might say, like, oh, yeah, it has these features. It has some black and white spots. It has, hooves and udders, and then like the ear shape. But actually, this is like just a post hoc rationalization of why we think this is a cow. Under the hood, our brain does not have very simple rules like these, where we have some kind of binary tree, kind of tree-based rule structure where we actually understanding things. It's very similar. I think some cognitive neuroscientists have like looked at what kind of activations are happening in our biological neural networks, and you often see very, I think these are from Deep Dream, but very similar like pattern activations of like how we identify something as a specific object is also very opaque. And then if you kind of apply this kind of reasoning to thinking of robotic systems, it's oftentimes very hard to define strategies or rules for, let's say, something as simple as tying a shoe. If I asked you right now, how would you teach me how to tie a shoe? There's probably a million different ways you could try to think about going that, and none of them would probably convey to me exactly how it just feels right to you, unless you've perhaps taught a toddler recently. And in general, right, I think there's oftentimes for every kind of general rule you can come up with for some scenario, there's a counterexample of like something that breaks that rule. So in general, it's just very hard to map very black and white definitions to the complexity and like the scale of the real world. And finally, and this kind of relates to the previous point though, is just Sutton's bitter lesson about scale. I think what Richard Sutton really believes in is that methods that scale with compute are the only kind of methods that will prevail in the long run, because even if you have shortcuts that use, domain expertise, you have researchers like yourselves that are in the space, and you think that, hey, this kind of inductive bias could really, help us solve this task. But then for the next task or the next task, that same inductive bias might not hold. So the only way that you can be sure that you have a system that will monotonically increase in performance over time is that if you have a method that leverages more data and more compute. And I think we've definitely seen this trend in other fields, in computer vision, in language modeling, as well as in reinforcement learning for self-play. And so I think the ingredient that seems to have been working very well is high capacity, very descriptive models, but also very large, high quality, diverse data sets. And I think if you have a method that can leverage both of these things along both axes, you have a very high chance of success when you're operating on a very large scale. So I hope I was able to shed some light on the kind of reasons why I'm fairly bullish towards end-to-end learning and why I think it's a very exciting direction to go. Um, I think that the next part, I'll try to set up some preliminaries on just the problem definitions and just some preliminaries, and then I'll dive into some of the recent work on my lab and how that maps back to these 4 points, and then dive into a bit more technical detail there. So I guess one, I'll start with, I'm assuming most people here are familiar with like the MDP definition and imitation learning and reinforcement learning, but I'll give a brief overview just in case. So in a standard MDP, you have an agent acting in an environment where the agent is able to influence the dynamical system by sending actions. And from the environment, you'll get a state in the form of an observation as well as a reward. Here you see in the bottom is that MDP, a different form of that we just saw, where instead of observing the true state, you'll sometimes observe an observation. This could be a camera image, LiDAR stuff, LiDAR images, depth images. It could be force feedback. It could be low-level state from proprioception. And in the setting, though, the setting that my lab most commonly operates on is if your observation is from pixels, you have a high dimensional RGB image, and then the action will be a continuous control vector where you're sending either torque or impedance control or positional control. In these kind of MDP settings, then there's kind of different ways you might think of solving this kind of problem to create a policy that can act well and generalize to new scenarios. One way is just applying supervised learning to a good offline data set that you have. This is worked in many other fields. How does it work in our robotics field? This works quite well, I think, under certain assumptions. If your training distribution is very similar to your test distribution, this could work quite well. The challenge, though, that sets kind of this decision-making problem apart from other kind of static supervised learning domains is that you start to get compounding errors. No matter how well you might try to make sure that your initial states in your test distribution might correspond to your training distribution, even minute errors will start to compound and exaggerate over time, which means that you get further and further off. You're basically kind of doing open loop planning in a closed loop setting. I think might be a good analogy. And as soon as you get off course by a little bit, you kind of are no longer have any guarantees. You're far from your training distribution, and your supervised learning, your imitation learning policy can't really recover very well without certain tricks. So perhaps another perspective to take on this is to use reinforcement learning. Reinforcement learning is in the setting, we'll focus mainly on value-based reinforcement learning. You use a critic network that estimates the goodness of each state by learning a value function or a Q function, which is in my current state, how good is this particular action proposal? Under these settings, you kind of train on entire trajectories where you know the reward that happened at the end, and then only using that reward, you try to update using dynamic programming your estimates of the Q functions and value functions of how well you are in current states. And then during inference, you use those value functions for planning. As you kind of think of different actions to do, you can query your critic network, see which are the best actions you might take, and then you take those and execute those and roll them out. The issue with this is that actually executing those on policy rollouts is very, very expensive. As you can imagine, if you have some kind of learned value-based network, a value network, and you have a policy operating on that, and you're kind of querying exploration actions, and you're trying to execute this in the real world, that can be very dangerous, very unsafe, and also very expensive. So model-based RL tries to get around this by learning the model directly from the data. Model-free and RL doesn't rely on that and just directly tries to optimize using that feedback in the most efficient ways possible. So yeah, that was a very, very brief and very quick overview of reinforcement learning, imitation learning, and kind of the setting that we're operating in. I'm assuming you all are already a bit familiar with that, so I won't delve into more detail. But I think that the next part, I guess I'll cover a few different areas that are very challenging today and some of the work from my group that's kind of sought to address those issues. As I mentioned, with the on-policy rollouts part, collecting that real online experience is quite expensive in the real world and perhaps unsafe at times. So one big driver is if we could utilize data that's cheaper to collect or that contains less supervision. In the imitation learning sense, a work from 2 years ago, is we thought of using play data. In general, when you're doing imitation learning, you need very high quality, successful demonstrations. So this is perhaps humans teleoperating a robot to do the task you commanded, or maybe it's training a RL policy from some underlying data set and then only filtering the successes only, and then having humans kind of do quality control to make sure that you have a unimodal, clean, desirable kinds of successes and use behavior cloning to clone those kinds of policies. The issue here is that that's very expensive, right? If you want a human doing the right thing and there's a lot of things you want to do, maybe it's expensive to get that human in the loop component. It's expensive to have the human labeling component, and it's also very perhaps it's very limited to the actual tasks that you were focusing on collecting for. Instead, we thought of if we can use play data, if you can just have human operators or another policy do behaviors in the environment that we know would be useful in like learning something about like the system dynamics or knowing something about cause and effect. You could use this large high quality offline data, even though it's not targeted towards specific tasks, you could still try to do self-supervised learning from that data set. So in this case, we collected a large play data set in an environment, and then we basically just relabel everything with hindsight relabeling as, everything is a success. If the operator was playing around trying to open the door and knock over some blocks, we would pretend in the beginning that, oh, you actually tried to open the door and then knock over the blocks, and then this is the trajectory that shows you how to get to that desired response. We found that adding a latent plan as in form of a hierarchy was important for that to get this to work. But in the end, from a very unstructured underlying play data set, you're able to learn a lot of diverse behaviors. From the reinforcement learning side, taking a similar like goal condition perspective, we had a work actionable models that did a very similar kind of philosophy in the Q learning setting. So by relabeling the goals, the states that were actually visited as the goals at the beginning when you're doing your Bellman update, we found that you could actually have no task definitions per se, but instead just view every single goal image as a new task and then train a Q function, a goal condition Q function on that. The one trick that we found was very important here is that unlike imitation learning, reinforcement learning struggles a lot when you have an underlying data set that is all positives. If everything you're telling your Q network is that, oh, great, this was a success, this was a success, no matter what you tell it, it's going to be very optimistic and it's going to overestimate the Q values across every single state, all actions, all tasks. So what we did is using a recent work conservative Q learning, you kind of only push up the true states and actions that were kind of seen, and you generate artificial actions and say that because we never saw those, let's just assume that that would have resulted in failure. It's an overly pessimistic look, but this helps regularize the Q function and make sure that you're not just saying everything is a success based on what you trained on. So besides for taking and learning from cheaper data, one thing that our group is excited about is actually leveraging existing expensive data sets more efficiently. We do have the luxury of having some real-world robot fleets that are collecting a lot of real-world experience, but it would be very unfortunate if we could only leverage, say, on-policy experience. What would you do with previous data that was collected using a different policy? How can we increase our throughput of our robot fleet, which even though we do have one, if you can speed up something by 2x, that's the same as if you had twice as many robots. So to push on this, we heavily leverage sim to real. Sim to real is when you train in a large scale simulation and then you try to somehow take the policies learned in simulation and then deploy them in the real world. While there are a lot of different approaches to this, one kind of cornerstone of what we've been working on is really focusing on the perception part. By using a cycle GAN to kind of transform simulation images into real world images, we are able to kind of learn policies that are robust to both simulation performance and real. Another part that we've been working on is concurrent control. Generally, in our manipulation environments, we assume a quasi-static environment, which is when you kind of assume that you have unlimited time for inference. You kind of send an action, everything freezes, you observe the state, you take your camera image, you pass it through your neural network, you run your actor, and then the return action, you then send it back, unfreeze the world, let it run, and then freeze it again. This is, of course, not how the real world works. Before we would actually make the world look like this by literally decelerating our robot arm at every single step to ensure that everything would be exactly the same as when we captured the image as when we sent it to the policy to get the next action. This, of course, slows things down a lot. It's very jerky. It limits the number of tasks you can do. Some tasks you require the robot to be in motion the whole time, such as tasks with friction, such as opening a door. If you're opening a door, you need to build up momentum to make that one whole smooth motion, as opposed to just jerking and moving 1 inch each time. So what we did here is we just enabled that our policy to start running inference even while the robot is still in motion, so that we can kind of predict where the robot would be when you're setting the next action. We found that this could really speed up our robot executions by almost 50% and unlock a lot more tasks that we couldn't do before. So right now I've kind of taken a viewpoint of imitation learning or reinforcement learning and the drawbacks of each method. Ideally, we'd kind of want the best characteristics of both. In imitation learning, you starting from a good data set, you can very quickly learn like a distilled version of your underlying data set. But with reinforcement learning, you continually improve over time with on-policy experience. Is there a way we can kind of get the best of both, start at a very high performance and then just get better over time? Well, classically, this has been pretty hard because for a variety of technical reasons. But in general, what happens is that when you switch from a behavioral cloning policy and you start just naively trying to send RL gradients and fine tune it, they're oftentimes very destructive. You'll see that for example, one of these plots on the right, you'll see that the imitation learning will start at good success. The minute you start fine tuning, it kind of drops to 0. And your kind of RL updates are just not useful for the behavioral cloning policies, and then it drops to 0, and then it slowly starts to learn again using the RL kind of gradients and updates. This is challenging, but one of the works that we worked on called AW-opt uses advantage weighted actor critic methods from there combined with different methods from the QT-opt method I mentioned earlier to kind of get the best of both worlds. One interesting tidbit here that drove a lot of the successes was just combining the benefits of the actor predicted actions with the critic predicted actions. In QT-opt, we do a sampling procedure where we basically find a batch of candidate actions, we use to query the critic, and we use that to kind of as the best scored action there as the action we use as the policy action. Here, one of the tricks that we found to be useful was to actually just add an actor predicted action to that batch, and that helped really well. There were 3 or 4 different tricks as well. If you're interested, I suggest you read the paper, but this was a big breakthrough for us to improve on IL plus RL. But in addition to just playing with the model and the loss components that AW-opt did, we also started looking at the data itself. Normally, when we execute kind of on policy data collection, we either only kind of use some kind of pre-trained policy or we use the exploration policy. What we kind of did here is we kind of molded the two by allowing some kind of initial good policy. It's not the best, but it's a reasonable policy to roll out partially, and then hand off control to an exploration policy. The reason this works well is that oftentimes, when you have hard exploration reinforcement learning problems, you might take a long time to randomly explore for a success. If you're using something like epsilon greedy, maybe you're oftentimes sending random actions and exploring and just getting really far off the path, whereas an initial good policy might be able to get you close to the goal, and then that kind of random exploration will get you back to the goal. What this top plot shows is just the different stages of a curriculum that this kind of learning can provide, where you have a good policy guiding you close to the goal, you explore a bit, your exploration policy is very confident it can solve the task when it's close, and then you move back a bit, and then you move back further until your exploration policy is the one doing all of the control. And the kind of intuition here is that in addition to making sure that the actor and the critic can play nicely in the architecture or in the loss itself, you should also make sure that the data is very conducive for learning for both the imitation learning and the reinforcement learning perspectives. And finally, this is a bit more future looking, but I think one thing that a trend we for sure have been seeing in other fields and robotics is that there's a ton of data now, very interesting data, very useful data, but not all of it is very conducive to learning for all tasks. And what we've increasingly been seeing is that we'd like to use more of this data, regardless of where it comes from, regardless of what was the original intention of that task. Maybe this comes from foundation models. Maybe it comes from large internet data sets like Reddit or Wikipedia or YouTube. Maybe we have some pre-trained models that we are on robot tasks, but they're from different policies, different kind of settings. We have no idea where they come from. Maybe there's demonstration data. Maybe there's intervention data when humans actually go and correct when a robot's about to do something unsafe. These are all very different types of data set sources, but we'd like to be able to take advantage and learn from these diverse data, even if particular data sets have particular advantages or disadvantages. Two recent works that kind of look at this kind of data sets that are on domain onto robotics. There's three main works. The first one is not from our group, but it's from my friend Suraj at Stanford. What they did was they take a large offline robot data set. They use language to annotate a small amount of it, basically grounding it back to what is actually useful in this data set. How do we have the useful language labels and understand what's going on here, and then use that learn model for planning, for MPC control. And that's one way to kind of ground a large robot data set into a different modality language. Another way is, what if we directly had the entire data set with language? What can we do there? And this was the BC0 work I mentioned, where our group used imitation learning to kind of learn a language condition multitask policy on a ton of on-domain robot data. And then the RL perspective here is, well, we have a large data set, but what if we had pre-trained value functions? If you view value functions as kind of distilling the knowledge of a large data set, these value functions allow you to kind of have individual planners that are very well attuned for the values of different tasks. And so here you can just query your value functions to see when you should, for hierarchical control, switch to the next task. You first open a drawer when the open drawer value function is Q value is high, and then you switch to picking something out of it, placing it on the counter, and then closing the drawer. You're using the value function the whole time to decide when you should be moving through those steps. But perhaps this is the most out there, I think, is what happens when you have off-domain data sets that don't really talk about robotics at all. From the language side, you have something like, or the vision side, you have something like CLIP. This is a model from OpenAI. It's trained on like language and vision data sets. You have a lot of understanding of all these random internet objects because it's trained on, Flickr or Reddit or any a lot of data sets that don't involve grippers or drones or legged locomotion robots, but they involve everyday objects. Perhaps there's some semantic understanding there at such scales about left and right, up and down, different colors. If there's a way you can actually use those representations and bring them into the robotic world, I think that's very interesting. And so what Clipport did was something quite similar. They used frozen clip embeddings without any fine tuning, and then just directly used those for control, and it worked quite well. A very recent work, I believe within the last week, was a work when they use autoregressive language models just pre-trained on Wikipedia, on internet text only, and then bring that kind of those transformers over to the trajectory modeling space. This is something like decision transformer. And they find that actually pre-training on Wikipedia helps a lot, whereas pre-training on, say, like an image GPT style loss doesn't really help. So I think there's definitely a lot to be explored here in like how to ground this internet scale data and knowledge into something that is useful for robotics. So I think this is definitely something to keep an eye out for. In summary, though, I think this was kind of my perspective on end-to-end robotics in a nutshell. We started out with 4 different reasons why I'm very bullish. It's worked elsewhere. Why not robotics? If robotics doesn't work, I think it's very interesting to figure out why it doesn't work. It's biologically plausible. The third reason is that the definitions are really hard. Mapping our human priors onto what the real world looks like is very challenging. So the thing we should trust the most is the data. That's related to the 4th point, which is Sutton's bitter lesson, that methods that scale with compute, that scale with more data, are the ones that will win. Whenever you have a system that uses many learning components, eventually the components that do not scale will be the bottleneck. And so that is why you need a system that will all scale with data. And then mapping that onto, I think, some exciting areas for robot learning. I think being more efficient with the data sets we use with self-supervision is a very exciting direction. There's actually making sure that when we do have access to real data or on-policy data, how can we make that more efficient? How can we have more data throughput? And then how do we leverage simulation at scale to make sure that's still useful for the real world? Then the 3rd point is how can we get the best of both worlds for both imitation learning, behavioral cloning style stuff, as well as reinforcement learning that can improve from more data. And then finally, I think this is the area I'm personally the most excited about, which is when we look at other fields, the really cool fast speed developments that are happening. When we see, pre-training on different tasks, multitask learning using internet scale data, I think this is where a lot of synergies are going to become really exciting when we can figure out like, okay, like this digital intelligence of like these internet tasks that don't have any physical grounding, when we add embodiment to that, what are the really cool directions that we can go in? And I think end-to-end learning for that will be, robot learning for that will be really exciting. Yeah, I think that's all I had for today, but I'd love to chat about it, get your thoughts, answer any questions. Thanks, guys.
Well, thank you, Ted. Very interesting talk, and your perspective on robot learning and end-to-end learning, and a little survey of all the different applications that you guys have done at Google. I think I see a question, so feel free to unmute yourself and ask.
Hi, Ted. Great talk. I think one general question I had is, most of the points you presented seem to be about utilizing existing data sets. Whereas, like, if you're at Google, I think it's very easy to use these large data sets. But, for people, like even in college, like, in university and stuff, we don't have access to these large data sets. So I think one general question I have is like, what do you think about focusing on exploration, or just focusing on methods that address the difficulty of data collection itself over assuming access to large data sets?
Yeah, thank you. I think that's a really great question, and that's a very common scenario. It's probably, I think it will be increasingly less common, but in today's day and age, yes, like high quality data, robot data sets that have exploration solved already are not something you can assume for free. So I think in the low data regime, there are definitely a lot of like technical challenges in both the algorithmic perspective and like how do you use like, curiosity or different kinds of like expensive human interventions to kind of drive successes. But also I think for us, when we're starting from scratch, for a new project, it's kind of figuring out the actual infrastructural challenges of managing clean data sets. Like I think all of the large scale data sets that we've produced, and some of them are open source, but getting to the stage where those are useful for learning, I would say 80% of the time has required like just cleaning the data, like fixing action spaces, fixing observation spaces, really weird bugs. So I think based on those two things, I would say optimizing for exploration methods that are able to kind of make sure that you can reuse all of your existing data. I don't know if that's clear or not. I think like on policy methods in general, I feel like need to be guaranteed that they can also work in the offline batch RL setting if you're doing RL. Is that clear?
I guess you're just saying that if you do run exploration algorithms, the data generated from that should be somewhat reusable, right?
Yeah, I think like, yeah, exactly. I think that is like the most important piece. Like if make sure that any data that you're using for exploration will not just like help your one-step update, but also be usable for like any future kind of learning you need to do on that exact domain, that exact robot, that exact task. I think methods that kind of are able to meet that criteria will perform better than those that do not, such as, PPO or something.
Okay, thank you.
Can I? Is somebody moderating, or should I just go?
Oh yeah, all right, go ahead.
All right, cool. Hi, Todd. So I had a question, and I mean, you kind of touched on this in the talk, but I'm just really curious, like, what's your perspective on, like if we actually want to train these extremely large scale agents on extremely large scale data sets, like where's that data going to come from, right? Like you hinted that maybe, maybe we use Wikipedia or maybe we use Flickr, but that doesn't quite get you everything, right? Because that data doesn't have actions. So like, obviously you're not going to learn everything that you want from the data. So, and it seems that even at Google scale, like some of the results that you've shown, they're obviously very impressive. But it still feels like in terms of the diversity of settings, right? It's not like I can just take an agent train on those data sets and, use it at UPenn, just run the same exact model and it will work on my robot or even if I had the same robot, it wouldn't work on my environment, right? So like, what's your perspective on how can we get data that's diverse enough for truly generalist robotic systems?
Yeah, I think that's a great question. I think there's two perspectives. One is you make as little assumptions as possible, actionless data sets. You assume off domain, you make no assumptions about morphology or task or whatever, and you just hope to kind of leverage the semantic understanding of the physical world and use that as some kind of like physical prior, as say like pre-training or as some kind of policy constraint when you're kind of like training a new policy, and then you kind of focus on the fine tuning aspect that kind of grounds that kind of general knowledge to your robot. And I think the other aspect then is just like, and this might be a bit challenging, is like actually I think this is a perennial dream of like, any kind of roboticist is to use like high quality, clean data sets from multiple labs, multiple robot morphologies. Look at something like RobotNet, or I think Stanford recently released another data set last year. And then actually use that to kind of create, like, you view that as like domain randomization when you're creating a single policy that can kind of work under different, that will work in your lab, in your lighting conditions, under your kind of object set, as well as in Mountain View here, as well as work in, UW or something. I think that is more challenging, and I'm not very optimistic that that's like a very scalable way, because, as I mentioned, like we tried to use data from, I think, Stanford, Berkeley in our lab, and like getting the data clean and just making sure it's compatible was like almost insurmountable. So I think the only way to leverage these large data sets is in this kind of like semantic understanding of like, when you push an object, here's just what's going to happen. If you grasp a bottle, you should grasp you shouldn't grasp from the cap, you should grasp from the side. These are kind of inductive biases that will kind of transfer between data sets, regardless of where they're sourced from.
But I guess doesn't that kind of go against the beginning of your talk where you said that we want these end-to-end models that we will just sort of train on large scale? But yeah, I guess like I see your argument that maybe like that's what we should do in the middle term, but how can we actually get to the final like sort of, like the right side on your plot over there, where we kind of, like we have no inductive biases, or like maybe some very weak inductive biases, but no handcrafted knowledge and truly generalizable models.
Yeah, that's a great point.
Maybe your answer is just that that's not going to happen right now, and right now we still are kind of like, we're not at that stage yet. We don't have that kind of data.
Yeah, I think in a nutshell, yes. Every single paper that any robotics group is going to publish is a heuristic. Any kind of method we propose is an inductive bias. It's kind of structure that we're enforcing that, I think in the long run, I hope is not needed. But to kind of get to the scale where like things like these kinds of scaffolds, these kind of crutches aren't needed, I think will take time. And so right now, I think perhaps my philosophy is that we should just be very cognizant of the shortcuts, the assumptions we're making, and the heuristics we're using, and just making sure that we're comfortable with them, and that these are crutches that will, that can scale in a sense. It won't be something that is only applicable to one small data regime or one small task or like something like that. It should be something that's like transferable. And I think utilizing pre-trained semantic knowledge from other tasks, other data sets is a crutch that seems stable enough to hold us for at least, a few years. It won't be something that breaks in like the next calendar year.
Yeah, that makes sense. Thank you.
Xiao, go ahead.
Hi, Ted. Thanks for your talk. Along the line of what you just, like your answer to Oleg's question, I was wondering, like what you think about large-scale human data sets. You said that using RoboNet, which is like a large-scale robot data set, you guys probably can have more generalizable policy, generalizable robot learning. But my observation is that there's like more large-scale and diverse data sets in the human domain than in the robot domain. So have you thought about like, or like, what is your thought on like transferring human knowledge to robots?
Yeah, thank you. That's a really great question. I think it touches upon a lot upon my like last point with like you have on-domain data and off-domain data, where on-domain is grounded robot data sets, perhaps with or without actions. Off-domain is like internet text, right? You don't even have any kind of physical interaction. And maybe like what you're searching is in the middle is like, it's kind of off-domain because it's not robots, but it's kind of on-domain because you still have, it's grounded in like the laws of physics of causality in like common, let's say, household scenarios. I think this is like perhaps like a very good sweet spot. Because you do have a lot of strong grounding, you have a lot of like guarantee that these actions are most likely interesting and useful for humans, which is what we care about at the end. So I would say like similar methods that you see performing well on like Wikipedia, like the same kind of methods I think should be applied to these human data sets. And the benefits should even be stronger, because like it's always going to be a trade-off between how on domain it is and how large the scale is. Maybe with Wikipedia, you have like random number, 1,000 times the data of your YouTube video data. And then maybe your YouTube video is also 100 times more than like your robot data sets. And maybe that's 100 times more than the data set you have for your specific robot on your specific tasks. So as you move along the scale, you have more data, but it's less useful. So I think, yeah, human data could be a very good sweet spot there.
Thank you.
Any last questions? Actually, I did have a question for you. So like it's kind of not specifically for your work, but like as a research engineer at Google, what's like, is there like an application that Google is looking for, or are you working for like generalist solutions towards problems? Like, is there like Google as an entity, do they like say like, oh, we have these problems that we need to solve, or is they just like, for the good of all of robotic learning, like we need to solve these type of problems?
I think it's a mix of both. Like we're part of Google Brain, so there's no like there's no direct consumers or products. I think in general we're just very Google as a company is excited about like decision making and like having like real world like cause and effect and like actually having an agent in the loop of interaction. That being said, we do partner with Everyday Robotics. It's a team out of Google X. They provide the robot hardware and like they have some kind of products that they're shipping. And we're providing kind of the intelligence for that. We do sometimes partner with say like Waymo or like Loon or other companies. But at the core, our team's main focus is just advancing the state of the art for robot learning on making sure that robots can do useful things. Down the line, who knows? Like I definitely am not speaking for Google here, but like if there's large consumer scale applications of generalist robots down the line, I think I'm hoping that my work can play a part in that. And I think is probably what a lot of us in the field feel.